Welcome back. Let's look at the next sections for complex number. Here we're going to explore the more of the geometrical um, visualizations of complex number, and then extend that to complex equations, which we call as you can say that locus, right? Okay. Now let's uh, walk through this, right? So locus, or the path traced by these complex equations. Let's try to explore this further. Now let's look at the first example. So consider modulus z equal to a 3. Okay. Now without doing any fancy algebraic manipulations, let's try to uh, put our focus on its geometrical properties. Just by looking at that, it simply means a point, or points in this case, the points that has a distance of 3 units with respect to the origin here. So if you are going to use the Argand diagram here, so just let me roughly show it to you, right? So basically it means um, all the points that is equal distant from the origin here. So that typically will trace a circle. So this equation indirectly represent a circle equation centered at the origin there. So this is the visual property or geometrical property of this complex equation. So try to interpret it geometrically first. We know that this basically represent an equal distance, a set of equal distance complex number on the Cartesian plane, or in this case on the Argand diagram, that has 3 unit distance from the origin. Okay, by collecting all the points that is equal distance from the origin, we will be able to trace a circle. So therefore, we can conclude that z absolute z equal to 3 represent a circle that is centered at the origin with a radius of 3 units. So I hope that is clear. Now, algebraically, how does it look like algebraically for some of you who are more familiar with algebra itself? Okay, now we will let z be x plus iy, where the x and y are all real numbers here. Right? The x and y are sets of all real numbers that can be found on the Argand diagrams. So we're going to substitute this into this equation here, the complex equation. So that will be x plus iy modulus is equal to 3. And then by modulus, it means x squared plus y squared is square root of this is actually equal to 3. And then to get rid of the square root, we end up with y squared equal to 3 to the power 2. And then that is an equation that represents a circle centered or center at 0, 0 in this case. If you want to write this more explicitly to show the connections to the center, we can write in this form. Right. So this is a circle, center at 0, 0 with a radius of 3 units from the origin, of course, from the center itself, right? So I hope that is clear at this point. So first of all, always try to interpret these complex equations geometrically first before we apply any algebraic expression here, right? Okay, I'm going to show you the next section soon. Next, let's look at example that involve the path traced by this complex equation. And next example is here. Okay, let's consider z minus 3 equal to a 2 now. Right? Now, before we can figure out what we are looking at, maybe it's best we can rearrange this into a form that we are more familiar with. Okay, so we can actually write this as 3 plus 0i here. Now, that indirectly suggests that we are looking at another circle equation centered at, so this is basically another circle equation. So I'm going to write that down, circle equation center at this coordinate here, which is 3, 0, with a radius of 2 units. Okay, now that's how the geometrical perspective of these complex equations should look like in this case. Now, of course, if you like to prove it using algebra, we can. In this case, we will let z equal to x plus iy in this case. So therefore, this can be written as x plus iy minus 3 equal to 2. So from here, we are going to collect all the real components together and then all the imaginary sections onto the other side. And then finally, we can rewrite this as, or we can create or generate the Cartesian equations that represent this complex equation. That is given by y squared equal to 2 squared here. So from here, we can rewrite in a more comfortable form that will give us more information about the circle that we are looking at. So from here, we are quite clear that this is the circle equations center at 3, 0, and then come with a radius of 2 units. Okay, so that is a confirmations that it must be a circle equation. Let's look at how it look like if we were to sketch it out. Okay, so this is a circle equation centered at the center of 3, 0. So this is 3, 0 here. This circle come with a radius of 2 units. So the radius is 2 units long. Okay, so I hope that is clear on the locus of a circle given in the form of complex equation. Alright, I'm going to move on to the next one soon. For the general form for any circle equations can be given by this format here. You can see that is z minus z1 equal to r, where this z1 is any point on the Argand diagram. So here I'm going to let z1 be a plus bi here. So where the I square is equal to negative 1. Alright, now I'm going to show you the algebraic manipulations one more time to prove to you that this is a circle equations centered at the point A, B in this case. Right? So I'm going to let all the sets of points that satisfy this complex equation as x plus iy here. And then we're going to substitute this into this equation as usual. R represent its radius in this case. And then finally, we can rewrite this as, okay, now that actually represents a circle equation. Alright, so this is a circle center at point A, B on the Argand diagram with a radius of R unit in this case. Right. Now that's how the circle would actually look like. So just let me show you the visual representations of the circle itself. Alright. Now generally this is how the circle look like. It's a circle that is centered at not the origin anymore. It could be any point on the Argand diagram. Okay, so in this case it's a Z1. So Z1 can be any point on the Argand diagram. The radius is measured with respect to the center itself, not with respect to the origin anymore. Right? I hope that's clear. And then we're going to look at if we have other example to work with, or we're going to revisit some other complex equation that represent a different geometrical setting. Example 2, let's look at what we given in this case for example 2. Okay, so in this example, we are going to sketch the locus of points represented by this complex equation. Right? And then you can quickly recognize that this is circle equations, but be very careful whenever we work with complex equation that represent a circle. First step is to rearrange this. So I'm going to rearrange this. Right, so rearrange it in such a way that we can identify the point, the center of this circle clearly, not by using this. Right? Instead, you have to put a bracket around this number to show that its actual center is located at 5, 3 instead of -5, -3 that we get from here. Right? So here we can conclude that this is a circle center at this point 5, 3 with a radius of 3 units. Okay, so that's how the circle would look like. Of course, you can prove it algebraically like what we did just now, but that's the purpose is not to prove it algebraically one more time. If you like, you can do it for your own practice. Right? Now, just let me show you how the diagram would actually look like. Now, there you go. We have a circle of radius 3 units centered at 5, 3 here. Now, that is the locus. So the locus is a path traced by all the sets of points that satisfy that complex equation. Now, in this case, the tracing of all the points represent a circle equation. Right. Now, I hope that is clear. We're going to move on to the next one. We will still have one last sections before we move on to the next example. Find the Cartesian equations of this locus. Yes. If you are interested to obtain its Cartesian equation for this locus, it must be a circle equation. Now, if you don't want to do it manually, you can straight away write down. This is a circle equations that has a center here. So the circle equations will be 5 x minus 5 square plus y minus 3 square, and then with the radius, which is 3 square here. And then if you want to simplify it neatly, it would look something like this, equal to 9. So you can either leave it in this form, or you could actually expand this here. You can actually write as x squared minus 10x plus 25, y squared 6y plus 9 equals to 9. And then therefore you can write that as 10x plus y squared minus 6y plus 25 equal to 0. So you can also represent the circle equation in this form, which is not in its completing the square form. Just by looking at this, how do I know that this is a circle? you have to try your best to complete the square so that we can obtain this form. Once you reach this form, we can conclude that this is a circle that has a center at 5, 3, come with the radius of 3 units. Alright, now that complete this example 2. Alright, now this is our last example of locus that does not represent a circle in this case. It might represent some geometrical property that you are very familiar with. Let's try to figure out what geometrical properties that this complex equation actually represent. Right? Now we will have to do a bit of algebraic manipulation. Maybe we are more familiar with the algebra setting instead of looking at this complex equation. Right? So from here, we're going to let z be any points on this locuses, which can be represented as such. And then z1 and z2 are basically points on the Argand diagram. So I will let z1 as a plus ib, for instance, and then maybe z2 as, let me see, yeah, maybe it's better if I write it down this way, and then z2 as let me see, c plus id. Yeah, it's easier for me to relate to those symbol here. So all I need to do now is to substitute all this set up into its original complex equation. Now that would yield this z1, which is a plus ib, Alright, let me try to see what we are looking at here. Oops, I think I accidentally put a square here. Let me clean it up. Alright, now basically both of these look like a distance, okay, sort of like a distance from a point from these 2 points with relations to this locus here. So take for instance, I will roughly make assumptions here. So we have a z1 over here, we have a z2, 2 points on the Cartesian coordinates. We are saying that the solutions to these complex equations are all the points somewhere here that has the same distance measured from these 2 fixed points. So for instance, the distance from here to here must be the same, and then the distance from here to here must be the same also. Now that indirectly look like a divider between these 2 points here. Alright, now we're going to find out more about these 2 points shortly. At this point, we know that it's sort of like a symmetrical line between z1 and z2. So it's z1 is a reflection of z2 in this case. You can say that. All right. Now we're going to simplify it further to obtain more information about this locus here. Right? So all we need to do is just follow the same routine here. Alright, so that's what we have obtained actually. And then of course, you can expand that. You do notice that the x square and the y square would cancel automatically. So all we left behind is just this one. Plus a square plus b square equal to negative 2cx plus c square plus d square and then minus 2dy. Right, now that's what we have. And then with a bit of grouping strategy, I noticed that we have both x and y on this side. So maybe it's best if I can group all the x together. For instance, I have x, and then I will have 2b minus 2d. Y should be equal to, now what I have here would be a square minus d square plus b square minus c squared. Now you do notice that this can be factorized further into this. And then this can be factorized further. Okay, and then furthermore we can write as this. Okay, now you will notice that here a plus d divided by 2. A plus d divided by 2 is basically because the z1 is ab here, z2 is cd. So if you take the sum of a and c, average it out, that is basically the midpoint for uh, midpoint, the x coordinate. I would say the midpoint for the x coordinates between these 2 points z1 and z2. So I can label that as, I can let this be the midpoint, the x component for the midpoint between z1 and z2, whereby this one here I'll label as a plus d divided by 2, whereby the y component for the midpoint between z1 and z2 is given by b plus, is it b plus c? Did I get it right? A plus d. Did I get it right? Let me check one more time. That will be a bd ad. I should be doing A with C then. Okay, so just let me change it. In this case, I think my order is not correct. So instead of doing this, maybe it's better to combine in this way. I think my combination is not that good in this case, so I'll try to change it. That should be a square minus c square plus b square minus d square. So that would be a plus c here. I think a plus c make more sense in this case. Okay, that would yield a plus c divided by 2, b plus d divided by 2 here. And then that is the x component for the midpoint between z1 and z2. Then that is a plus c divided by 2, whereby this one is actually b plus d divided by 2 here. Okay, so and then I can rewrite this as, you can actually rewrite this as a minus c xm plus b minus d ym here. And then by rearranging this to the left hand side, I will be able to obtain this x minus xm plus b minus d y minus ym here, equal to 0. And then at the end of the day, you will notice that we can rearrange this as y minus ym is actually equal to a negative a minus c divided by b over d x minus xm. Yeah, x minus xm. Okay, and then there's a very useful information that we can obtain from this form here. If you observe closely this gradient, so this gradient a minus c, okay, a minus c divided by b minus d is a reciprocal for this. Now, if I were to draw a line here that connect z1 and z2, now I will be able to obtain the gradient for z1 and z2. So the gradient for z1 and z2 is actually given by uh, b minus d divided by a minus c. And then we notice that this is a negative of the reciprocal. Therefore, that should represent another line that is perpendicular to the line that is connecting z1 and z2. I will label that as m2. You will be quite happy with the m2, which is the same as negative a minus c divided by b minus d here. Because if you multiply m1 with m2, that will yield negative 1. That shows that m1 and m2 is perpendicular to each other. Therefore, these line equations here represent a perpendicular bisector. So this complex equation here represent a perpendicular bisector between z1 and z2. That is the geometrical perspective of this complex equation. So I hope that is clear here. I have indirectly provide you with a proof as to why is it known as a perpendicular bisector. First of all, we have determined that the solutions to these complex equations lie between the points z1 and z2. Okay, they are equidistant from these 2 points here. And then next, I have proven that this line here that is equidistant between z1 and z2 is perpendicular to the line that is connecting z1 and z2. Therefore, as a conclusion, we call this locus as a perpendicular bisector between the 2 fixed points z1 and z2. Now, I hope that is clear at this point. So next time, whenever you see encounter this format, whereby your right hand side expression is not a constant, then that must be representing a perpendicular bisector between 2 points. Right. I hope that is clear. Now I'm going to move on with the example that apply this complex equation here. Number 3, to show how we're going to apply the theory that we have covered just now regarding perpendicular bisector between 2 fixed points. So this question state that sketch the locus of points representing, represented by this complex equation, absolute z equal to z minus 6i. And then thereafter, we're going to write its perpendicular bisector equations here. All right. Now, before we start, it's always best to write this in this form. So z minus 0 plus 0i, just to make some sense in this case, to the format that we have written down just now. Okay, so by writing it in this form, we notice that this is a perpendicular bisector between 2 fixed points here. So I can indirectly write down that my z1 is actually 0 plus 0i here, whereby my z2, the 2 fixed point, is 0 plus 6i here. Okay, and then this is a perpendicular bisector that we are looking at. Now, how does the equations look like? We will go through the same procedure here. So we will let z be x plus iy, z equal to x plus iy. So that will be x plus iy and then that will give me x squared here, and then this part will be x minus 6 square plus y square. And then indirectly we can cancel those terms as required. So what we have is all these terms has been cancelled. We only left with what do I have here? 36. So I have 36 here minus 12x minus 12x equal to a 0. Therefore, x is equal to a 3. And then this is indirectly a perpendicular bisector between these two fixed points here. Let me show you how it actually looks like. So you can see that we have a point 0, 0, which is the origin, and then another point which is a 0, 6 unit vertically upwards. And then we want to set up a perpendicular bisector between these two fixed points. It must be at the midpoint between these two points here that's located at 3 units here. So this equation is what we know as the perpendicular bisector for these solutions. Just let me check if I got something wrong. Oh, yep. Okay, I just noticed that. Okay, it's always good to check here. I noticed that I make a serious mistake here. Now I'm going to change the color here so that we can remember what mistake we have done, or I have done in this case. So that should be x squared plus y minus 6. I indirectly combine it wrongly. So from here, I'm actually getting 36 minus 12y equal to 0. My y is actually equal to 3. So this equation represents y equal to 3, which is a perpendicular bisector between these two fixed points, z1 and z2 here. Now, I hope that is clear to all of you. I'm going to check if we have the next questions to work with. Number 4 here. Find the Cartesian equations of a locus of z if we are given z minus 3 equal to z plus I here, and sketch the locus of z on an Argand diagram. Right now, quickly we can recognize this as a perpendicular bisector between 2 points that's located at the coordinates of 3, 0 and then 0, 1 here. Right now, that is quite obvious. Now we are going to work out its Cartesian equation first, and then we can try to sketch it on the Argand diagram. Right? So as usual, we're going to use the same definitions. We'll let z equal to x plus iy, and then substitute this into its complex equation. And then always combine it carefully so that we don't make any mistake like what I did just now. So this is 1 plus y I. Okay, and then after that we'll follow the same procedures of applying Pythagoras theorem here. Okay, so that's what we have at this point, and then we know that we can cancel all the x squared and y squared. So this one we will have a 9, and then that will be 1 plus 2y instead. And then after rearranging, we will have y equal to, let me see, there's a 4 minus 3x there. Okay, so this one will be the Cartesian equations that represent the perpendicular bisector between these two fixed points located at z1, 3 plus 0i, and z2 equal to 0 plus I here. Okay, I hope that is clear. Let me show you how to sketch, or I indirectly already sketched that, just to let you see how it looks like. So this is how the perpendicular bisector for this complex equation look like. All you need to do is just sketch a straight line passing through the y-intercept or imaginary intercept at 4, and then the real intercept at 4 over 3 there. Yep. And then that is the sketch that we need, marking the fixed point here. Okay, I hope that is clear. We're going to move on to the next example. There's one more section I forgot to cover here. Now, what if we also require that the real z be equal to 0 in this case? Okay, so if the real part is equal to 0, now all we need to do is just go back to the drawing board here. If the real parts for the z is equal to 0, therefore our z is only I, y. Okay, so if this is only I, y, we will have a y square here only, and then we will have another 3 here. So just let me work that out. If the real part is equal to 0, this is what we have. So we only have I, y minus 3. The same thing goes here. That is, the real part is 0, so there is only 1 plus y I here. And then all we need to do is square this plus 9 equal to 1 plus y square here. And then if you simplify that, we know that the y square can be cancelled out, and then eventually you only end up with 2y is equal to 8, y is equal to 4. Okay, now since y is equal to 4, and then the real parts for this z is equal to a 0 here, therefore we are looking at just one specific point at 0, 4 here, which is actually somewhere here. Now that will be the only locus if the real parts for this z is equal to 0. Now I hope that is clear. That is our last section of example 4. Right? Now I will move on to example 5 now. 5. Here we have a complex number z is represented by the point P. Okay, by the point P. Given that it satisfies these complex equations, we know straight away that this is a circle equation centered at 5, 3 with a radius of 3 units. So the first question is to sketch this locus. Okay, sketching this locus should not be a problem, but as usual, before you sketch it out, we must rearrange this neatly. So for A, it's better for us to rewrite like this. From here, we can identify the center for this circle. So this is a circle center at 5, 3 with a radius of 3 units. Okay, so I hope that is clear. This is how the diagram look like. Right? So it's a circle centered at 5, 3. Radius 3 units. So we are very clear that it's touching the real axis at one point here, because the radius here is actually 3 units. Okay, so I hope that is clear for A. Now for B, find the Cartesian equations of this locus. Okay, finding the Cartesian equation for this locus is should not be a problem. You can either substitute this indirectly into the original complex equation, or you can write the Cartesian's equations directly. That will be x minus 5 square plus y minus 3 square must be equal to the square of its radius. Okay, so therefore we have x minus 5 square plus y minus 3 square must be equal to a 9. Now that will be the equations, the Cartesian equations that represent this locus here. Okay, so I hope that is clear. Now the next one, find the maximum value of argument z in the interval negative pi and pi, exclusive in this case. So the maximum value for the argument. Now whenever they mention the argument z, they are saying that what is the angle make uh, with respect to the real axis that will give us a maximum angle in this case. So just let me draw that down. So basically it looks something like this. Now the maximum angle that we can have, the minimum will be somewhere here. The minimum will be somewhere here, whereby the argument must be equal to 0. You can also have this particular argument somewhere here, or you can have, okay, just let me show you. You can have an argument somewhere here, yeah, which could be like theta 1, or you can have another argument somewhere here, for instance. Yeah, somewhere here that is touching this part here. That would typically be larger than this particular argument that I'll label that as theta 2. So you can see that theta 2 is much more larger than theta 1, and then that is the largest argument that we can have. So therefore, we can say that theta 2 is the maximum value of the argument z. All right. Now the question is, how do we find this argument here? Right. So there are many methods we can use here. Okay, I'm going to show you using geometry coordinates, or using its geometrical perspective in this case. All we need to do is just work out. Okay, basically just work out this this particular angle here. Just let me sketch it here. It's easier to see. So I'm going to divide this. It must be a bisector of this angle here. Right? So all I need to do is work out this angle. In order to work out this angle, and then by the way, because this is a tangent, so it must be a 90 degree. Okay. So here, in order to get my maximum argument, I can actually work out this angle here. This angle, which is similar to this angle here. These two angles are the same. And then I can actually make use of the typical trigonometry ratio to work with this. Right? So it's very obvious that now I'm going to call this alpha here. It's easier to relate. I will say that sine alpha, I can use sine alpha because I knew the, sorry, not sine alpha, I think I used the wrong one. I can actually use tangent alpha in this case, because I have the horizontal length, which is 5 units, and then the vertical length is 3 units. So that is equal to 3/5 here. Therefore, I should be able to obtain my alpha to be arctangent or tangent inverse 3/5 here. And then the maximum argument, don't forget, maximum argument for z must be equal to twice of this alpha, which is the same as twice of this inverse tangent 3/5 here. And then if I were to key in into my calculator, hopefully it will give me the answer there. Just let me try. That is tangent 0.6. Yep, correct. Okay. 0.6 is it? Yeah, correct. Oops, there's an error there. Hold on. Let me try one more time. My calculator is always giving me a problem here. Okay. Alright, so that is typically 30.96 times 2. 30.96 times 2. And then it will give me this 61.92 degree there, right? So you can either leave it in term of degree, but since the answer need to be in term of a radian, then you can convert this to radian. Like in my case, I don't really have a proper calculator to calculate this, so therefore I need to time a pi. So time a pi, and then after that I need to divide by 180. So that answer in radian is 1.08, three significant figure. Then that will be our maximum argument for z, right? And then it's located within negative pi and a pi here. So I hope that is clear. That's the answer for a C here. Okay, now we're going to work with D now. Okay, for D, let me clear all this. We don't need this anymore. All right, now for D, we need to find the minimum and maximum value of z. So what do they mean by minimum and maximum value for z? So basically that means the distance measured from the origin itself. So what is the shortest distance measured from the origin to the path, the circle, the path of the circle here. So you can see that the minimum must be here. So the minimum magnitude of z must be from the origin to here, and then usually it must pass through the center here. And then the maximum value for this must be the longest here, because if you pass it through here, that will be the longest magnitude of z that we can get. So therefore, I'm going to work this out. The minimum value for this must be equal to this one here, minimum. Okay, so how do we work out this value here? Is very simple, just by using geometry again. We know that this length here, I'm going to label that as OA, for instance. Now the minimum magnitude here is the same as OA, the magnitude of OA minus of the radius for this circle. So the radius for this circle, in this case, is 3 units. Okay. Now the length for OA is quite easy to obtain by using Pythagoras theorem, because this is 3 units and it's 5 units. So that is 25 by 9, 34. So it's root 34 minus of 3 here. So just let me check the number here. So 34, okay, and then a minus a 3 here. So that is around 2.83 units. That's the minimum. Okay, and then the maximum is, so you can see that the maximum of this absolute value for z is basically the you can see that is basically the minimum. The minimum for this plus twice the radius. Basically is 2r here, and then that would be 6 plus 2.83, which will give you 8.83 units. So I hope that is clear. Always approach C and D geometrically. It will be much more easier. Of course, is there another way to actually obtain this? Yes, there is. You can actually use a calculus method, right? That one I'll leave it for some other time, right? So if you're interested to explore that, by all means go ahead. Okay, now I'm going to move on to the next example. Number 6. Okay, let's look at this. Given that a complex number z satisfy the equations here, now you notice that this is also a circle. Find the minimum value of the absolute complex number z and the maximum value of that. Minimum value and the maximum value, right? So the first step is always to recognize the circle with the correct center first. So let's restructure this correctly. That should be a 12 plus 5i here. Okay, and then we know that this is a circle, center at 12, 5, radius of 3 units. Okay, now once you're done, all you need to do is it's best to sketch it out. Okay, let me see whether I have the sketch. Yeah, right. So this is how the circle look like, center at 12, 5 there. So we are about to find the minimum and the maximum value of the z. When they say minimum or maximum value of the z, they are indirectly saying that the minimum distance from the circle itself to the origin. Okay, so just let me show it to you here. So you can see that the minimum, okay, just let me put it down here. Hopefully it will go properly. Okay, it's not very clear here, but please forgive me on that. Just let me try one more time here. Yeah, okay. Now, in this case, it's not very accurately drawn due to my internet connections here. Let's assume that this line actually passes through the center here. All right, okay. So I'm going to mark a few points here, and then this is the origin. Now, the shortest distance from the origin to the circle is basically here. Now, this one will be the minimum absolute value from here. Or A is or C is the minimum. I'll just call this OP. So OP will be minimum, and then OQ will be maximum. So the same methods apply here. All I need to do is to find the minimum value for this absolute value, minimum. That must be OA. The length for OA subtract off with the radius itself, which is 3 units. And then I know that this is 5 unit, this is 12 units here, and then this one must be 13 unit. So 13 unit minus 3, which is 10. So minimum absolute value is 10, whereby the maximum value for Z, you would notice that quite easily. This is 10 unit plus twice the radius. So the radius is 3. So in this case, we have 16 units. All right, and there you go. I hope that is clear. As usual, I mentioned that you can actually apply calculus to solve this if you're interested to try. Example 7. All right, it's a long example here. Right. Now find the Cartesian equations of a locus of z if it satisfies this complex equation here. And then next, we're going to sketch the locus of this z on the Argand diagram. Now, and then finally, we need to find the least possible value of z, which is the minimum value for z here. Okay. Now, before we start, we recognize this as a perpendicular bisector between two fixed point there. So the two fixed point is here. You can see that the perpendicular bisector between these two fixed points, which is located at 3, 0, and then the other one is 0, 1. So it must be a perpendicular bisector there. So to sketch it is quite easy. Now to find the equations for this perpendicular bisector is quite easy, other than using the method that I've shown to you. So here I'm going to show you another approach to obtain the perpendicular bisector by using a coordinate geometry approach. So first of all, I'm going to find the midpoint, midpoint G. So midpoint G can be obtained from here. Okay, so that is typically 3 plus 0 divided by 2, and then 0 plus 1 divided by 2, and then that will be 3 over 2, and then 1 over 2. Just let me check whether that is correct. 1.5 and then 0.5 there. Yeah. There you have it. There is the midpoint G. And then next, I know that this is a perpendicular bisector. Therefore, the gradient M1 and M2 must satisfy this relation. Okay, so I'm going to work out the gradient M1, which is it's quite obvious. It's a negative gradient here. Is 1/3, negative 1/3. Right? We don't really need to use any fancy formula here. And then therefore, I can conclude that the gradient M2, which is perpendicular to line EF, must be equal to a 3 here. And then knowing all this, then I can find out the perpendicular bisector. So perpendicular bisector is given by y minus half 3x minus 3/2 here. Okay, so if I want to write in the y-intercept form, then it will be 3x minus 9/2 plus a half here, and then that will be 3x minus 8/4 here. So just let me check whether I got it right. Negative 4 here is a positive gradient, and then there you have it. That would be the perpendicular bisector equation. And then lastly, we need to find the least possible value of z. So least possible value of z, what it means is, what is the shortest distance measured from the origin actually. So the shortest distance. You can see that measured from the origin, shortest distance from the origin to the line there. So the only shortest distance that we can think of is the distance from the origin perpendicular to this line here. Okay, now that will be the shortest distance that we can obtain here. Alright. So how do we actually obtain that? Okay, there are many ways to work with this. Okay, now I'm going to show you the coordinate geometry methods in this case. Now we notice that this perpendicular bisector cut the real axis at this point here. We can actually get that from this equation, which is 4/3. This is actually 4/3, and then this is a right-angled triangle, and then we need to find this particular distance here, which is the shortest distance possible, right? So we know that this length is here, but the thing is that we have no idea how long this is, right? So if we knew this length, then we can obtain this using Pythagoras theorem there. But anyway, we don't really need to know that length at this point. All you need to do is figure out this angle here. Okay, this angle. This angle is the same as this angle here. Therefore, I'm going to make a remark. Tangent theta is basically the gradient for that perpendicular bisector, which is equal to m2, which is actually equal to 3 there. Okay, so that is our tangent in this case. And then I'm going to redraw this diagram again so that it looks something like that we can look at it from this perspective. Okay, so this is the D that we are interested to find. This is the O, and then we know that this is 4/3 units from here. And then we have already figured out this theta here. All we need to do is work out the D from here. Okay, work out the D from here. Now the D is basically 4/3 sine theta. Sine theta. Alright, now there are many ways to do this. We know that tangent theta is equal to 3 here. Right? Tangent theta is equal to 3. And then therefore you can work out the sine theta by drawing another triangle here. This triangle is different from this triangle here. This triangle, we draw it to represent the ratio of tangent. So here I'm going to draw it here. That is, this is theta here, which is a 3. 3, 1. So there's a tangent, and then therefore there is 10 square root here. Sine will be 3 over root 10. And then from here, I can substitute this into here by 3 over root 10. And then that would actually give me 4 over root 10. So you can actually leave it as it is, or basically if you want to rationalize that, that is actually root 10 over 5 there. And then that will be our shortest distance, the least possible value of z, which is the shortest distance from here. Right. Now I hope that answer the last part here. Okay. All right. Now that's all for this section here. Okay. Now we still have one more types of locus. Other than circle, perpendicular, bisector, we also have a locus relevance to the argument itself. Let's look at how this locus actually look like. Right? Okay, so the general format is argument z minus z1. Z1 is a fixed point on the Argand diagram. Is equal to theta in this case. Right? So let's look at how this locus would look like. Now, let's start with the first one before we look into the more general form. If you are given argument z equal to pi over 6, how would that locus generally look like? So just let me show you how the drawing look like first. Okay, now first of all, we will have the real axis and the imaginary axis. When they say argument z, basically they are saying we are actually measuring the angle starting from the origin here, and then because the angle is pi over 6 is positive, so we're going to measure the angle counterclockwise. Okay, counterclockwise 30 degree. So therefore it should look something like this. Pi over 6 here. And then the locus is basically a line that passes through the origin and then make an angle of pi over 6 there. Right. Now that will be the locus for this example here. So I hope that is clear. Right. Okay. Now let's look at what else we have. Right, now next, if you are given argument z plus 3 plus 2i equal to this, how would that actually look like? Now the idea is exactly the same. We are looking at the principal angle of 135 degree in this case, right? But it does not make reference to the origin anymore. In this case, we are making a reference to that new fixed point, which is 3, 2 in this case. Right? Just let me get the Argand diagram here. Okay, we have that Argand diagram. So from here, we are going to restructure this properly so that it can fit in this format, just like the one that we did just now. So we're going to write this one down as argument z minus 3 minus 2i instead is equal to 3 pi over 4 here. Okay, and then these will be the points of reference where we're going to make that angle. So we're going to look for this. That is 3 units to the right and then 2 units down. So somewhere here, this will be the point, the fixed point z1 here. And then from here, all you need to do is draw a reference line. Draw a reference line. My reference line it's not very horizontal. Forgive me on that. So it's horizontal line, and then this one will make 135 degree. Assume that this is your origin now. So it make 135 degree with respect to this point, and then the horizontal line where the angle is measured from is this horizontal line now. That is actually y equal to -2 here, and then that will be somewhere here, and then the angle will be 3 pi over 4 here. Okay, now bear in mind it does not go exceeding this point here. So that is our locus that is represented by this complex argument equation. So it's a 3 pi over 4 or 135 degree measured from this new horizontal line now, counterclockwise, because the angle is positive. Right? So I hope that's clear. Okay, right. Lastly, we're going to combine all the locus together, and then try to figure out which region does all these locus actually representing by looking at regions overlapping by all these locus. Right? Okay, let's look at the first example. Now, instead of having equal sign, this is a circle equations, but instead of using equal sign, it's less than equal to. Now the same thing, all we need to do is rearrange this properly so that we can recognize the center of this circle. That is 4 plus 2i. Okay, so we know that this is a circle equation. Circle equation center at 4, 2 there with a radius of 2. So all we need to do is start by sketching this circle. Okay, now that is a circle. Now centered at 4, 2, come with a radius of 2 unit. Oops, I think I pressed too fast already. Okay, now here we go, with a radius of 2 units. So this is 2 units. Okay, and then the only difference between equal sign and less than is we are saying that all the sets of points that satisfy this inequality actually fall within that circle. So indirectly, this inequality represent the surface, the surface that is found in the circle, inclusive of the outlines. So therefore, by shading this region, so this whole region is actually representing this inequality. So the shaded region represent the solutions to this inequality complex equation. Right. Now I hope that is clear for the first one. Second one, we are given this inequality. We can recognize that this is a perpendicular bisector between these two fixed points. Okay, I'm going to get the perpendicular bisector line now between these 2 points 4, 0 and 6, 0. So it's obvious that the perpendicular bisector will be passing through that midpoint 5, x equal to 5 here. And then there we have it. Now if this is equal sign, yes, it's a line. If it is less than, it actually shows a region, regions on the left hand side. So the region on the left represent the solutions to this inequality. So I hope that is clear. It's a very simple task to identify the region represented by this inequality. Okay, I'm going to move on to the next one. Okay, argument. We know that argument is basically a line that is created based on certain argument. Right? So in this case, we're going to extend that idea further by identifying the region represented by this inequality. So here we are looking at argument that is less than pi over 4, more than 0 there. Again, it's best to rewrite this one more time to indicate to us where is the points of reference. So the points of reference in this case is the fixed point is 2 plus 2i. So 2 plus 2i is point D here, according to my marking. Okay, and then this horizontal line will be our new real lines to measure the angle here. So we are measuring 45 degree with respect to this point, with respect to this green horizontal line. And then therefore the line will be somewhere here. Okay, and then it says that less than, more than or equal to, so starting from here, and then go all the way up to 45 degree here. So this is 45 degree. Right? And then the region that it actually represents will be all the regions covered by this sector here. Right. Now that will be the region represented by this inequality. I hope that is clear. And then lastly, we're going to combine all this inequality together under one roof to see where is the regions that are all of them overlapping. Okay. As you can see, these are all the results that we have obtained previously. Now we are combining all that region under one conditions, which is a collective conditions. We are trying to find the overlapping areas between all this region here. Number one, which is a circle. The surface area is a area of a circle. And then the second one is the regions on the left hand side of this perpendicular bisector. And then lastly, for the argument, is the area subtended by this sector here. So putting all this into one diagram, it would basically look something like this. And then where is the overlapping regions? Where is the common regions that they overlap? So it's quite obvious in this case. All of the region, oops, I think I used the wrong here. All right. So you will notice that the regions overlap by all this region here is here. So that is typically a triangle. Regions subtended by or overlaps by all these solutions is here. Now I hope you are able to visualize this. And then that will conclude the whole chapters of complex number. All right. So if you like what you are looking at, do press the subscriptions button and then click on the notification bell so that you can get updates, the latest updates of my videos. All right. And then if you like the videos, give a thumbs up. All right. Thank you very much for your support. I'll see you guys again.